Good day, ladies and gents, and welcome to our next video lecture on the design of steel structures, where we're going to be getting into the design of beam columns today and looking at how to design these according to SANS 10162 Part 1, the South African Steel Design Code. So follow within us in the notes, and I'm going to be having a look at the various procedures that are available for beam column design. So just an overview of what we're going to be going through. First, a look at beam columns in practice. So where do you have members that experience both bending and compression, or bending and tension? And then beam column behavior, elastic behavior, plastic behavior. The main focus is strength checks. That will be the bulk of what we're looking at, and then how to do the different strength checks. And then we're also going to be looking at second order effects and tension and bending. Now, make sure you've also got your SANS 10162 Part 1 code with you, and then you can add the notes to that you'll see me making on the screen. Now, you often end up with members that experience both compression and bending, or tension and bending in practice, whenever you have unbraced structures or multiple forces being applied to a structure. And even, for instance, if you're having a look at these diagrams, here we've got a column, but the load being applied to it is eccentric, so that'll introduce a moment by its eccentricity. And then here on the right hand side we've got a column, and there's a crane that applies lateral loads and vertical loads at a distance. So that applies then, that causes beam column behavior up at the top, and various other sections, various other types of structures can experience both bending and compression. For instance, top right, there you can see a column carrying very large plate girders, and then the connection causes an eccentricity in the column, so causing a moment in the column. So now here's some other examples. Here you've got a portal frame, and this is a very, very typical example of a beam column, because the portal frame is continuous, so the rafter will carry moments into the column and apply an axial load. So portal frames always are designed as beam column members. And then right hand side you'll see a multi-story structure where you'll have moments being exerted. It depends on the type of connection you have, how much eccentricity is caused. For instance, if you have a cleat connection like that, then the eccentricity is larger. We can assume it's, for instance, about 100 mils from the face. It'll depend on the cleat size and the cutting dimensions and tolerances, etc. But our eccentricity is a certain amount from the face. If we have a web cleat, then web cleats deform, and we can assume that the load is basically applied at the face of the column, because there's bolts going from the column into the beam, and there are then bolts from the cleat into the column. So bolts into cleat from column and bolts into beam from cleat. Now, continuing on, we also then can have cap plates, etc. This is a far less common type of connection, but you could have something like that, and you would conservatively take it at the edge of that plate or the edge of bearing, although in reality the load is probably applied a little bit further to the left. Now, when it comes to deriving the equations we're going to be using for design, from basic first principles, if you're looking at the stress in a member, so the maximum stress anywhere in a member is just force over area, axial force over area, plus moment over elastic modulus. So this is for an elastic stress. And so, as I said, you'll have your axial stress plus your moment stress, and then this will give us some maximum stress, and we want to make sure that at the maximum position we are now less than some amount. But if we want to start playing with this equation, and then we're going to take this to a plastic design, because our design code is a plastic design code. If we divide through by our yield stress, we end up with force over area times yield and moment over ZE times Fy, so modulus times yield stress. And this ends up in as the ratio of stresses is the ratio of the force to the yield force, and the ratio of the moment to the yield moment. And now, if there is no residual stresses, then the stresses will be at yield, and so we'll take the stress right up to yield. We're going to assume the maximum is now our yield stress, and so the ratio of stresses must be a maximum of 1. So is it 100% stressed or less? And we end up with force over yield force and moment over yield moment. So that's from pure first principles elastic stress design. So now we can then add on biaxial bending to that. So now we add on axial force, moment about x, moment about y. And just be a little bit careful. These subscripts are confusing because the one y is an axis and the other y is a yield. So just be careful with that. So now the equation above forms the basis of the interaction equation that is used to test whether beam columns are sufficient, whether they're strong enough. But we have to consider additional factors such as deformation of members between nodes, imperfections, and plastic behavior. So we've got to generalize that equation to account for reality. The fact that these are not perfect members, they do deform, they do have imperfections, but we do allow plastic behavior. And ultimately what you'll see in our design code is this equation here. And this forms the absolute basis of everything we're going to be doing in terms of the checks. So we're going to be having a look at stresses and forces axially, stresses and forces for moment about strong axis, stresses and moments about weak axis, and checking that all of them together will give us a member that is suitable. But firstly, before we go into that, let's just think about plastic behavior when we try to incorporate it. Here we see a beam, a doubly symmetric I section, and a stress distribution through it. Now, if these are our stresses, we can break this down into an axial component and a moment component. So what will happen here is, if we take the area this acts over times yield, this will give us where the axial load is carried. And that will be in the middle of our section. And then also we have a moment section. Here we've got a force, and then some sort of lever arm between them. And this will then give us give us the moment. There. So if you want to calculate then from the stress distribution, what is the moment it is carrying and what is the axial force it is carrying? The axial force is simply its area, 2 times some distance, yn, above or below the neutral axis, times thickness of web, times yield. So this would give us a area times stress, giving us a force. And then if we have a look at I'm just rubbing out some stuff so you can see it. If we have a look at then the moment, we're going to end up with moment from flanges and moment from web. So there will be some force due to the flanges. Let me draw that the other way around to be consistent. Some force due to in the flanges, some force in the web, force in web, force in flanges. And the moment is the sum of all of those. So once again, all this is an area times a distance times a stress. So stress times area gives you force times distance. So this is a lever arm, and then this is a lever arm as well. And you can go through the derivation of that yourself, but it's just simply force times distance, and then adding up all the different components: compression force, tension force, etc. So then we will end up with all the different forces and sum it up. And it'll be the same even if you have an asymmetric section. For instance, now, if this is not symmetrical, what you would have to find then is a similar scenario, similar behavior, where you're going to have some sort of area in, let's call it an area in moment, area carrying the moment, and area carrying the compression. And then the area carrying the moments has got to be the same. So area carrying moments in compression equals the area in moment in tension. So we have equilibrium, and then also the area in compression you would find from based upon how much moment is being carried. So you can then start applying this to asymmetric, well, singly symmetric sections and the likes, just by finding a sum of forces to carry the moment, and then the area in the middle carries the compression load. Now, continuing on, this is what I was just explaining on the previous slide. So should you need it, all the derivation is provided there, well, the simplification. But now, when we get to beam column behavior, we have to include various behavior that occurs due to the buckling behavior about the different axes. Now, this diagram may be a bit difficult to understand, but all it's trying to illustrate is it depends on how both the moment and the axial load interact. So, for instance, if you have the load on the one axis and then the in-plane deflection on the other. If you have linear elastic beam, number one, and you load it, as your moment increases, your deflection increases. So that's quite easy to see. But then we have a bilinear elastic plastic beam, because we know a linear elastic beam doesn't exist, because then you'd have infinite stresses that the section carries. So we simplify it to, as soon as it hits yield, we assume the whole thing has yielded. So then we get line number 2, where it goes up and then it flatlines. So as soon as it reaches a certain rotation, we then have a yield moment. So it goes up and then it flatlines, and then we end up with number 2. But then we also have the fact that there are some residual stresses in the section. And so now we start ending up with elastic plastic behavior, number 3. So there is a transition. It's not a perfect and sudden transition from plastic, from elastic to plastic. It's actually a progressive onset of material. So that is now all our bending behavior. But now let's have a look at what our column does. So if we have an elastic column, we load it, and then suddenly it buckles, and then it just deflects infinitely. So then that behavior we get there from our column. But now let's start putting all of this together, and what you will find then is that you then start ending up with a real, a column interaction where both the moment and the axial load is taken into account. So if you have an elastic interaction, so that's number 5, the fact that you've got this column behavior and the moment behavior start coming into play. And so you end up with that behavior there. And then if you start having plastic interaction curves, so this is a purely plastic section taking where it's rigid and then suddenly it goes plastic, you have now that column, that behavior there. And if you put all of that together, you get to a beam column. So this is what we are actually designing, a beam column down the bottom here, where this is our in-plane deflection. So how much does it deflect under load? And this is for a combined axial load and moment. So the fact that axial load causes buckling, moment causes deflections and buckling, there are residual stresses and a whole bunch of things together. This curve at the bottom is what we are trying to calculate, and how does all of these buckling behaviors, how do they interact? And that's what we are looking at now. And so there are 2 main ways we're going to be dealing with this. And this is to do, firstly, with, we've got to classify our section. If it's class 1 and 2 I-shaped section, we use this equation, and then all other sections, we use the equation on the right. All other sections except class 1 and 2, I and H-shaped sections. So this would be class 3, I and H, and channels would normally fall in there. We typically don't design sections such as angles and the likes for bending, and so generally what's on the right hand side is channels in class 3 or 4 I and H sections, and on the left hand side you've got your class 1 and 2 I and H sections. So when we are going to apply these equations, there are 3 different ways we apply it. We are going to check for cross-sectional strength, overall strength, and lateral torsional buckling strength. And I have added a little static key, a little star there. And everywhere you see that star, you know that each time you do a check, that value is different. So if you're doing check A, B, or C, everywhere you see a star may have a different value. So you need to recalculate those each time. The MUs and the MUXs and the other things stay the same, so they stay the same from check to check. But everywhere you see a star, you will find you must update that value for each check. And so you may have 3 different values. They're often only 2, but you may have a different value each time for those. And so, as I was saying, this is where that equation comes from. We're now in section 13.8 of the code, and we now need to design for this, and always checking that it's less than or equal to 1, i.e. it's at 100% or less of maximum utilization. And so there are various factors we're going to look at discussing, the U1s, and then all these different factors we're going to start looking at. Before we get into the different checks, we need to consider the interaction of the slenderness of the section. So firstly, one of the ingredients is this beta value. And beta is for biaxial bending. So when you have MUY, when you've got a bending moment about the y-axis, you need to include this. And this is for accounting for the slenderness of the section. And lambda y is non-dimensional slenderness parameter about the y-axis as per compression. So this is the non-dimensional slenderness about the y-axis. So you can get that from previous calculations when we for compression members. So what is the non-dimensional slenderness about the about the y-axis, and this is less than or equal to 0.85. This is to account for beneficial effect. So this is just trying to optimize and make this equation as simple, as efficient as possible, give us a stronger member and as efficient a member as possible. So it's less than or equal to 85%. So it's not 1. It's not saying it's we're combining the total effect of stresses about y and the total effect about stresses of x because of moment redistribution and plastic stresses and various other factors. So now, continuing on, we're going to start now with the 3 checks. So remember I was saying you had to change those values with the stars each time. And so here's how we're going to do them. If the capacity of the member shall be examined for cross-sectional strength, beta is 0.6, so we're actually given a fixed value. And then CR is as defined in 13.3 with lambda equals 0. So now, what does that mean? That is a short column. Short column, i.e. KL equals 0 meters. It is checking stresses, this check. We are just checking stresses. The effective length does not come into effect. You always use, no matter whether the column is 1 meter or 100 meters long, use an effective length of 0 meters. It's a short column. And the exact same thing then for the beam. If you use MR as defined in 13.5. Now what is 13.5? It is laterally restrained beams. A laterally restrained beam is a short beam. It is a beam that does not experience lateral torsional buckling. So once again, our KL equals 0 meters. So we're checking stresses. We're checking at the maximum moment and the maximum axial load position. What are the stresses? Buckling does not come into it. And then we've got other factors we're going to check now. U1x and U1y are as defined in 13.8.4, but not less than 1. In this check, we are checking stresses. So we don't ever reduce to account for buckling. This U1x and U1y account for buckling. There is no buckling in this. So we do not ever have U1x and U1y less than 1. It could be greater than 1 to account for the fact that there are deformations causing P delta effects, which we'll see soon. So it could be greater than 1, but if we calculate a value of U1x and U1y less than 1, we don't take it ever less than 1. So now, what does that look like? Well, firstly, just coming back, cross-sectional strength, members in braced frames. You only do this check for braced frame structures. If you did it in a structure which is not braced, that's actually okay. It's not a problem to do that. It's just a waste of time, so you don't need to worry about it. And what do we mean by braced frame? Well, if you look at the left-hand diagram, that's an unbraced structure. So if you are designing the column on the right-hand side, a sway structure, an unbraced structure, means that there are significant lateral deflections between the nodes you are designing. So if I'm designing the right-hand column, it means there is some deformation between its two ends that is significant enough to account for. If I'm looking at this diagram, a braced structure, there cannot be lateral movement. This is prevented by the bracing. So there is no significant lateral movement between the top of the column and the bottom of the column. That is prevented from happening. So therefore, you do not need to account for those lateral movements, and stresses then may govern. Stresses may govern, so then this check becomes important. So this is why check A is important for this, because we are checking stresses in this first check primarily. It's based on stresses and limiting at the position of maximum moment or maximum axial load. So if you want to look at what is a definition of a braced structure, this comes from 1381 in the code. In this clause, a distinction is made between braced and unbraced frame. A frame with direct axing bracing is classified as braced when its sway stiffness is at least 5 times that of a frame without direct bracing acting. So if you have the structure and you add a load and you see how far it deflects, then you add bracing and see how far it deflects. If the deflection is now 1/5 of what it used to be or less, then it's a braced structure. But we're going to cover that more in future lectures. So cross-sectional strength check. This is a very simplified representation. We're checking that axial stresses plus bending stresses, we are still limiting, we're less than or equal to our yield stresses. At the position of maximum axial load, we are not violating this principle. You forget about buckling. Buckling does not come into this check. But when we start doing other checks, then they start coming into play. For instance, now we get to overall member strength. Now, CR as defined in 13.3 with the value of K equals 1. So it doesn't matter what your effective length is normally, K is 1 now. You always use K equal 1, except that for uniaxial strong axis bending, you check the CR equals CRX. If you have uniaxial, i.e. it's bending about only strong axis, it's only got an MUX, there's no moment about the y-axis, then your capacity is based upon the compressive resistance about the x-axis. It doesn't matter if it can buckle about y, you only check x. Now continuing on. MR is as defined in 13.5, i.e. short beam. KL is 0. Then continuing on the factors to account for deflections, U1x and U1y are as defined in 13.8.4 for members in braced frames, and taken as 1 for unbraced frames. So if you have sway, if there is some sort of deflection at the start of the node and the end of the node, if the two nodes can deflect relative to one another in a significant portion, in a significant amount, you take it as 1. If it's a braced frame, you take it as a calculated value. So now, continuing on, let's see what that looks like. So here, for instance, if we were taking a uniaxially loaded member and we loaded it, what will happen? It'll get to the stage where we check the buckling in this manner. We check it where it buckles basically forward, like so. Same thing now with bending. We are checking bending, no buckling. Remember, we're checking a short beam. until it fails in this manner. When you see this, it may start becoming clearer. Why are we putting these two failure modes together? So for uniaxial bending, it's a forward failure, and for bending, it is a forward yielding. It's reaching its plastic capacity. So that's why we are putting these two together. They are failures in the same direction. They're causing the same type of failure mode. So as bending failure occurs, it makes CRX worse. As CRX occurs, it makes bending failure worse. So these two interact, so that's why we put them together and check that they are occurring at the same time. So then we move on to check C. C is as defined in 13.3 and is based on weak axis or torsional flexural buckling. So that is FEY or FEYZ. So we're going to check a compressive resistance, but we're checking a weak axis or a torsional flexural buckling, not FEX. Then moment, this is now a long beam. And what I mean by long is you design it as you normally would. You account for the effective length. If the effective length is 1, that's fine. I mean, is 0 meters, then that's fine. If it's a laterally restrained section, fine. Design as a laterally restrained beam. But typically speaking, you now use the KL value that you have. Then moving on, U1X and U1Y are taken as 1 for members in unbraced frames and are taken not less than 1 for members in braced frames. And so there are some requirements depending on whether they are braced or unbraced sections. So just be careful of those ones where it's unbraced and braced. You have different values you use. So what does this look like? So we are now checking the minimum compression failure of CRY. Remember, CRY is buckling about Y, so it looks like that. We have got a CRZ, which is a torsion failure. So that would be something like that. It is a torsional failure. It is a twisting failure. Or we end up with a lateral torsional failure. So the whole section buckles outwards and twists at the same time. So that is then a lateral torsional failure. And when we check our beam, we are checking a lateral torsional failure, like so. So we need to check for that behavior as well. Now it might becoming clearer why we're doing this check and how they interact. We are checking how lateral torsional compression failure and lateral torsional moment failure influence each other, because as the one occurs, it'll force the other one to occur. So they make each other worse. So that is why we do this check. However, when it comes to I sections and H sections, if it's a doubly symmetric section, we don't actually have to check FEYZ directly, because here's the equation for FEYZ. This whole long equation straight from our code. But if we take that equation and we put into it a doubly symmetric section, so that's our x0 and y0 is 0, i.e. our centroid and our shear center at the same place, and we plug in and we just play with the mathematics a little bit. You can follow all of this through. What you'll find is most of these terms disappear, and you'll find FEYZ equals FEY or FEYZ equals FEZ. So we don't have to directly check FEYZ. All we do is check Y and Z, and that'll sort it out, because we have inherently then checked FEYZ, the lateral torsional failure. So you'll see we don't normally have to check that third one. We check the first two for a doubly symmetric section, and we will inherently have checked the third one as well. So that is then a lateral torsional check, and that we need to do. Once we've done those 3 checks, then we move on to biaxial bending, or just a bending check. And then even for uniaxial bending, you do this. Check. All you're checking that if the moment if the axial force is really, really low, this basically just becomes a beam. So this protects you from the time where you've got a low axial force, you end up designing it as a beam, so you don't account for the beneficial interactions of beam and column and effective lengths and all those sorts of things. So you're just checking that moment over moment of resistance is okay, and then you add in the moment about the other axis as well. You'll see there's no compression term. So this is, really comes into play when axial loads are low. And as I said, you do this as required for either you design the member as it is. If it's laterally restrained, design it as laterally restrained. If it's laterally unrestrained, which most case it is, design it as laterally unrestrained. And so we're just checking stresses in this case, or capacities. We're making sure that the interaction of only moment is not going to fail our beam. And if we put all of that together, we get to a simplified representation of something like this. So on our one axis, we've got our ratio of force over axial capacity. On the other axis, we've got our ratio of moment over moment capacity. And when we do our checks, we will have some sort of interaction. Let's say now our ratio of force and our ratio of moment, and we have a solution that is there. We now need to check for the different interactions about the different axes and see how they make sure that they fall into this feasible zone here. So we check, does it satisfy cross-sectional strength? A. Does it satisfy overall and lateral torsional buckling strength? B and C. And then does it satisfy biaxial strength? And so that is for low axial stresses. You'll see only for low axial forces that governs. And we want to make sure that our feasible solution is within all of those. For instance, if we were there, we would have passed some, failed others. We have to satisfy all of them. And one thing you'll find is depending on the effective lengths and the behavior and various other things, all of these, the slopes and the positions of these lines will change each time. So this will then give each time you may find a different criteria governing. The equation we use for designing all other members looks like exactly the same as we've discussed above, except you'll see the 0.85 and beta values missing. But otherwise, when you are designing all classes of sections except class 1 and 2 I-shaped sections, it's exactly the same equation, just minusing out the factors in front. And you'll see those factors give class 1 and class 2 I-shaped sections higher capacity. That's because there's good redistribution of moment and the likes in them, so they're a bit more efficient, where all the rest with slightly lower capacity. And just remember, I-shaped refers to both I and H sections. Now, one more thing we need to just discuss quickly is the value of U1. And what this U1 value does is it accounts for the deformations of section, accounting for the second order effects due to the deformation of a member between its ends. So here's the equation we need to use. Now the problem is when you have a look at that, initially you have no idea what that is and why it's there. So we're going to have a quick derivation, well, approximate derivation of where that comes from. First thing we have is omega 1 for the axis under consideration. So that is very similar as omega 2, which we've looked at previously, is the influence of the shape of the bending moment diagram. And then we have CE, which is the Euler buckling load. CE is the Euler buckling load. So if you have a look at this equation, what you'll see is, just as the form of it, as our compressive load increases, this factor then increases as well. So as we get closer and closer to the buckling load of the column, the influence of buckling becomes much greater. The strength decreases as the compressive load increases. So buckling becomes a big deal. And as buckling becomes increased, the deformations between ends becomes increased. So if you have a look at this diagram here, if you have a column with a moment m at the bottom and then a ratio of that km at the top, and then an axial load as well, p, when the member distorts, it follows some curve, some deformation along its length, and it'll reach a maximum displacement somewhere, for instance there. Now what will happen there is that we want to make sure we account for the extra P delta moment that occurs. So there is a bit of extra moment due to the fact that now P is acting at some distance Vz, and we need to account for that. So we need to approximate the influence of this, because we will, for instance, analyze a portal frame. We'll get the moment at the top, we'll get the moment at the bottom and the deflections, and we'll analyze it. But we haven't calculated the deflections all the way along the length, and we need to account for those deflections along the length now, which aren't given to us by our structure analysis model necessarily. We could add nodes and actually get it from there, but normally you just have a moment top and bottom, which we then will put into this. So the deflection is as shown there, and I'm going to do a rough derivation of where that comes from. So as the load approaches the critical load CE, then mu L approaches pi, meaning the deflections tend to infinity, i.e. as the compressive load increases, the stiffness and bending resistance decreases. So simple case, if we've got a simply supported member, uniform moment each side, and then it deflects, then we have a P delta moment of Cu times delta. So that gives us the maximum moment. So this M we'll get from our finite element model, and that's what we'll be designing for, but we actually need to increase its influence to get it up to M subscript M, maximum moment. So we need some sort of amplification factor. It's difficult to calculate the maximum deflection delta for every column, so instead we calculate approximate relationship for all columns. So this is a simplified general case because we don't want to work out the deflections each time. So if we have some amplification factor, as shown here, and we just play with the maths a bit, but we assume then that the value of delta, the deflection, is very small, so mu plus cu delta, this term becomes small, so we end up with that term. From first principles, the deflection of a simply supported beam is as follows, which is approximately equal to the buckling load, if you work with that. And then what we do is when we plug that all in together, we end up with an amplification factor in the form of what you saw earlier. So as our force tends to our buckling force, so our amplification factor tends to infinity. And the case of equal moments each side is the worst case scenario. So with a lower moment one side or double curvature, the value of delta decreases. So this is where we get the SANS 10162 part 1 equation for modifying the maximum moments as the following. So we adjust it by omega 2. Same concept as omega 1. We adjust the capacity based upon the shape of the bending moment diagram. Uniform moment worst case, double curvature much better. So the values of omega 1 in the code are as follows. So for members not subjected to loads between supports, so that will be when you have a member and you have a moment and a moment. Nothing applied along its length. We use this value then, kappa. And then kappa is the ratio. Kappa is the ratio of the moments as previously calculated for bending elements, max. The ratio of the minimum to maximum moment with positive and negative to suit double or negative, double or single curvature. But if you have a member subjected to distributed loads or a series of point loads between supports, so if we have our beam, and either we have then a series of point loads, or for instance we have a distributed load on our beam, then we will use an omega value of 1. So that would be worst case. And then members subjected to concentrated load or moment between ends, then we will have our beam, and either then we will have a single point load or a single point moment somewhere along the end. And then we will use a value of 0.85. If we have multiple loads, 1, and if we have no forces applied along the length of what we are designing, then this value, and you'll see it's 0.4 and up. So this is the more conservative, well, that gives you the highest capacity. Continuing on. So if we have axial tension and bending, same story. We have, for instance, a member. If it has a force on it, we need to calculate its tensile capacity, and then same story as above, we combine these in different ways. So if it's class 1 or 2, that's our moment of resistance. So this once again is a short beam because it is a it doesn't include buckling, but then the clause below, this is for a long beam. So very similar to above, either you design it for stresses, checking it as a short beam, or you do the equation below, looking at it as a long beam. And remember, the tension resistance is not based upon lengths. You don't have multiple tension resistance. You'd look at just where the maximum tension resistance is, or sorry, the minimum tension resistance is, and use that, either gross or net section, etc. So yeah, so that brings us to the end. So just a quick revision if you were getting confused about buckling, because we've been discussing about buckling a lot. Just remember with this, remember FEZ torsional, FEY buckling to the side, FEX buckling about x-axis, FEYZ torsion, and that we showed. To check it, we will check either one or the other if it's a doubly symmetric section. So doubly symmetric, the FEY and FEY and FEZ account for that. And then, yeah, if you've got an asymmetric section, counting for that. So that's just a quick revision because we've been discussing all along. So that takes us through the design of beam column elements. So remember, there's a single equation which we then use in multiple ways to get the capacity. And when we check that, make sure that all of them pass to make sure that our element is sufficient. And we'll go through a detailed example shortly to see how to apply this. Thank you.